Welcome to another action-packed calculus video. In this video, we're going to look at section 3.3, increasing and decreasing functions, and the first derivative test. So our bullet points determine intervals on which a function is increasing or decreasing, and then apply the first derivative test to find relative extrema of a function. Let me set it up like this. So here's our xy axis. Oh, my pen's a little glitchy today. And let's say we find, we set our derivative f prime equal to 0, and we get an x value, a critical number. We'll just call that point C. That's right here. And let's say we put point C back into the original position function, and we get its y value, f of C. So we know there's a point floating out here in space, and we're trying to figure out if that point is a minimum, a maximum, or maybe neither. Because remember, just because it's a critical number, we're not guaranteed that it's a min or a max. So to figure out if this floating point is a min or a max, we're going to look at the first derivative. That's why this is the first derivative test. And you know that point C is going to chop us up into intervals. We'll have negative infinity up to point C, and then from point C all the way off to infinity. And we'll pick some number in that interval, and we'll plug it into the derivative and see if it is positive or negative. If it's positive, that means we have positive slope and our function is going up. If our derivative put in there, or our test value put into the derivative is negative, that means our function was going down. And then from the other side, from C to positive infinity, we'll pick any value in there and we'll plug it in. And let's see, maybe in this interval, our derivative is positive. That means our function is swinging back up. And if we go from a negative derivative to a positive derivative, we've just figured out we have a min at the bottom of that valley. Or let's say that maybe our this interval over here, our derivative is positive going uphill. And then on the other side, we plug in a test value and it's now negative. We know we have a hill, and on the top of the hill is a max. And there's also the possibility that maybe our function is increasing on this interval, and then in the next one, it's right back to increasing. So that would be neither a min nor a max. So our derivative test, we're going to plug test values into the first derivative to see which way the function is headed. But first, let's get some technical jargon and definitions out of the way. In this section, we will learn how derivatives can be used to classify relative extrema as either minima or maxima. Relative min or max, maybe not the global, but we'll find the peaks and the valleys. First, it's important to define increasing and decreasing functions. And it says here a function f is increasing on an interval when, for any two numbers, x sub 1 and x sub 2, in the interval, x sub 1 being less than x sub 2 implies that f of x sub 1 is less than f of x sub 2. And in option 2, we are decreasing on an interval when for any two numbers, x1 and x sub 2, in the interval, x sub 1 being less than x sub 2 implies that f of x sub 1 is greater than f of x sub 2. Is that perfectly clear? Okay, let's move on. No, I'm just kidding. Let's take a look at this from a graphical perspective. Here's xy axis. Let's just look at, we'll do the first one and then you'll see what's going on. You figure out the second one. It says here our function is increasing, and it says x sub 1 is less than x sub 2. That means it's less than it. It is to the left of it on the positive x-axis. So here's x sub 1 is less than x sub 2. This implies that the output f of x sub 1, that's right here, is less than f of x sub 2. So that means f or x sub 2's output is higher, it's going to be up here, x sub 2's output. If I connect those dots, we can see that that is increasing. In the second part, decreasing, notice the only thing they changed, this inequality stayed the same, this one reversed. So the outputs changed places. So, whoa, x sub 1's output would be up here, x sub 2's output is now the lower one. And if I connect, whoa, dang it, if I connect those dots, now we are back and our function is decreasing. So a very technical jargon kind of a definition, but if you look at it graphically, it becomes crystal clear. So a function is increasing when as x moves to the right, the graph goes up. X is decreasing when the graph moves, or the function is decreasing when the graph moves downward. For example, look over here in the figure. It's decreasing from negative infinity to this point A, whatever that is. Constant on an interval. Here we got a flat spot. our derivative would be equal to 0. And then we have an interval where we're going back up because our derivative was back to positive. And blah, blah, blah. Here's our theorem. A test for increasing and decreasing functions. Now, this is not the first derivative test yet. This is just setting it up. So it says let f, our function, be continuous on a closed interval from a to b. It's differentiable on the open interval in between a and b. If the derivative is positive for all x's in that interval, the function is increasing. If the derivative is negative for all x's in the interval, then it's decreasing on the whole interval. If the derivative is exactly equal to 0 for all the x's in the whole interval, not just at one point, then we have a constant function. All right, we get to do an example. Find the open intervals on which this function is increasing or decreasing. Okay, step one, we need to find our critical numbers, and we're going to do that by taking our derivative, f prime, and figuring out where it's equal to 0 or non-existent. So that looks like it's going to be a 3x squared minus, this will be 6 seconds, 6 over 2, or 3x to the first. And we're going to set that derivative equal to 0. So let's see here. I'm going to put a pair of red parentheses around there and ask myself, what can I factor out of each term? Looks like a 3x comes out, and that'll leave us an x minus 1 equal to 0. And we set our first factor equal to 0, and we get x is 0. And our second factor equal to 0 gives us x is 1. So I'm just going to put them up here for safekeeping. So I can erase, well, I want to keep my factored derivative. That's going to be important in a little bit. So what we have now, let me bring out a little chart, a little table. We've got these critical numbers. I'll sort of block them off here in red. These are going to chop up our intervals. So our first interval, negative infinity to the smallest of the numbers, that would be 0. Next interval, this one left off at 0, this one picks up at 0, and that's going to go to the next critical number 1. And then our last interval is going to go from critical number 1 to infinity. Okay, next we're going to pick a test value from each interval. That test value will go into this derivative. We will figure out the sign, if it's positive or negative. The number does not matter, and we'll come to our conclusion. So if you remember from pre-calc, when we're testing intervals, some of my favorite numbers, like for this one, would be negative 10, because it's easy to multiply and divide by 10. For the last interval, we'll do positive 10. Now here we're sort of boxed in. Well, not really. There's infinitely many numbers between 0 and 1, but we'll just play it safe and pick 1/2. First test number, negative 10, I'm going to plug it into this term. 3 times a negative 10 is negative. And if I put my negative 10 into the second term, negative 10 minus 1 is also negative. If I multiply those two negatives, I get positive. What's the conclusion about the function? If we have a positive derivative, our function is increasing. Next, 1/2. Let me get a couple of sets of empty parentheses here. 1/2 goes in the first term. 3 times a half is positive. In the parenthesis, 1/2 minus 1 is negative. A positive times a negative is negative. Negative functions are going downhill, so I know this one is decreasing. Last one, positive 10 goes into the first term. 3 times 10 is positive. Parenthesis, 10 minus 1 is also positive. Two positive numbers multiply to a positive. Positive derivatives tell us our function is increasing. Now, before I bring the figure down, I'm going to sort of spoil the first derivative test because this is a great example to show it on. Here, we have a critical number 0. Something's going on at 0. To the left of 0, our function is increasing, so graphically it looks like this, and then we hit that point. On the other side, the next interval, we are down to decreasing. So it sure looks like here we just found a local max. I'll put local on there. That is a local max in that interval. And now over here, let me go to black ink. At 1, something is going on, so we've got a dot at 1. To the left of it, our function was decreasing. and then we get to that dot. And on the other side, from 1 to infinity, our function changes to increasing. So what we just found here is a local min. So let me bring down the graph. And there it is. You know, we could have put the 0 into the original function and got our y output of 0. We'd know we're at the origin. If we put 1 back into the original function, we would get, looks like, negative a half. So that is going to greatly help our ability to graph nice graphs. Oops. Okay, let's see what we got next. Just some guidelines here. What's going on? Okay, guidelines for finding these intervals. Let f be a continuous function on our open interval a to b. To find the open intervals on which the function is increasing or decreasing, here are the steps. Locate the critical numbers of the function in the interval. Remember, that is where the derivative is 0 or non-existent. Use these numbers to chop up your test intervals. Determine the sign of the derivative at any one test value inside that interval. Use Theorem 3.5 to determine if we are increasing or decreasing on the interval. It says these guidelines are also valid when we have an A to B interval, when we have more than one critical number. One critical number gives you 2 intervals, 2 critical numbers will give you 3, and so on. But then it does say a function is strictly monotonic on an interval when it is either increasing or decreasing on the entire interval, or when it's increasing on the entire interval or decreasing on the entire interval. For instance, let me bring this down here, x cubed. X to the third, if we set it equal to, or take the derivative 3x squared, we set that equal to 0, we get x is 0, so that would be a critical number to investigate. But if we pick a number to the left of 0, we see the function increases. On the other side of 0, the function is still increasing, so that critical number led to neither a min nor a max. So that is a monotonic function, and we did not find a local min or local max. That strictly monotonic will also be broken if you have a piecewise function and a flat spot in there. Like here from 0 to 1, our output is strictly 0, so we're not monotonic anymore because we do have a constant spot. Up next, now we get to the official first derivative test. And it says after you determine the intervals on which we're increasing or decreasing, it's not difficult to locate the relative extrema. For instance, the figure 319. Okay, yeah, this is the exact, I just pointed this out on the graph of that after the example ended. The function here, that's the one from example 1. It has a max at 0, 0 because we increase to the left and we decrease to the right. Similarly, the function has a min at the point 1 negative a half because the function decreased to the left and then went to increasing to the right of it. The next theorem makes this more explicit. So here is the actual first derivative test. To set it up, c is a critical number of function f that is continuous on our open interval containing that point c. If function f is differentiable on the interval, except maybe at point c itself, then f of c can be classified as follows. If the derivative changes from negative to positive, then we have a min. And let me go down to point this out on the graph right now. We went from negative derivative going downhill. On the other side, we went to positive going uphill. Negative to positive means we have a valley, and that means there's a min. If the derivative changes from positive to negative, so first our derivative was positive going uphill, we hit our point, and then we change to downhill, that's going to be a relative max. If the derivative is positive on both sides or negative on both sides, then the derivative, that point f of c, is neither a min nor a max. So here is our strictly monotonic going up, and then it hits the point, and then it continues to go up. Or we could be going negative derivative down, hit our point, and continue going down. So that would be monotonic, no relative min or max. All right, and here we go, another example. Find the relative extrema of a half x minus sine x on this interval. So of course, step 1, we need to find those critical numbers. We're going to need a derivative. F prime of x equals half x derives to a 1/2, sine derives to cos. we take the derivative and set it equal to 0. And since the cos is negative, I'm going to add it. So my cos is going to be positive, but I want that to be on the left, so I'm going to write it here. Cos of x is equal to positive 1/2. That is our derivative. Okay, where on the unit circle is cos equal to 1/2? So here, cos values are x values, so I know I'm going to be in quadrants 1 and 4. And then I remember back to my pre-calc days, we're going to have this would be positive 1/2, and we're also going to have one down here at positive 1/2, but at a negative angle, or remember we'd go all the way around. And this occurs at pi over 3. Pi thirds gives us our x value of positive 1/2. And then this would be 5 pi over 3. 5 pi over 3, because we're finding the intervals on the unit circle. Our first angle is here to pi over 3, and then our next interval will be from pi over 3 to 5 pi over 3. Yeah, and it does say interval 0 to 2 pi. So we'll have another interval. Let me switch to blue ink. There's another interval. So we got 1, 2, 3 intervals. So our first one, 0 to 1/3 pi. Next up, 1/3, that's a terrible 3, to 5/3. And then finally, finishing off our trip around the unit circle, 5/3 to 2 pi. All right, we are going to need a test value from each of these. Now the first one, a real nice one in there would be pi over 4, right in the middle of that quadrant. I do like to stick to the coordinate axes if I can, and a good one in here from 1/3 pi to 5/3 pi. We could do 1/2 pi, but I also like pi. Pi is a good one right in there. And then for the last one, 5/3 to 2, that's this little piece here. The only good one I think in there would be that 7/4 pi. 7/4 pi. And now, of course, we're going to put these test values in. And I'm going to make my eraser a little smaller here, because I'm going to put those into that first derivative that we found there to see if the output, I'm going to get rid of that 0, and put question mark, is it positive or negative? And here this is a constant, so it's 1/2 minus. We're just going to put our test values in here for cos. So the first one, 1/4 pi, both sine and cos are √2 over 2. So 1/2, and think about that as the square root of 1 over 2 minus the root of 2 over 2, that's going to be negative. So our function is decreasing. Cos at pi is -1. But we have this as a minus, so that's going to be minus a -1. That'll change to plus. 1/2 plus a little more is positive. And our function is increasing on that interval. 7/4 pi. Cos, just like here at 1/4 pi, 7/4 pi has the same cos, positive square root of 2 over 2. So that's going to be the exact same output as our first interval, negative and decreasing. So we found the intervals like we did in example 1. Now the directions here were to figure out the mins and the maxes, the extrema. And when I read this, it says find the relative extrema. It kind of sounds like they want the y values to go with them also. So let's see here. Our first one at pi over 3, comma something, we went from negative decreasing to positive increasing. So that looks like we have a relative min. Now let's find the y value that goes along with it. So we go back to our original function. 1/2 times x, and we're putting in pi thirds. So that's going to be 2/3 pi. And then minus the sine value at 1/3 pi. That's √3 over 2. Ooh, that's not a very pretty y value. We could get it, I guess, as a common denominator. 4 pi minus 3√3 over 6. 4 pi minus 3√3 over 6. Again, we got our x and y values, so we did figure out we got a min. And let's hop over to this one. Something's going on there at 5/3 pi, comma something. And what we had happen was a positive derivative or increasing. We hit our point, and then we decreased. So that is going to be a relative max. And let me clear a little space. We'll figure out the y value that goes with it. So 1/2 times that x value there is going to be 10/3 pi minus the sine value there, and the sine value at 5/3, that's going to be a negative √3 over 2. So minus a negative will turn that to a plus √3 over 2. So this one will be even uglier. Denominator 6, 20 pi plus 3√3 over 6. And there's our min and our max. Ooh, let's see what the book looked like here. There we go. So yeah, our max was a small negative number, min bigger positive number. Yeah, we found the min and the max. Then these were our critical numbers. First step, find the critical number that gave us our suspected mins and maxes, and then we tested them out. Okay, now this one, as soon as I see the fractional exponent, we are going to have this one. Our derivative will be in the form of a fraction after the deriving is done. So here we're going to set our numerator equal to 0 and also our denominator equal to 0 for when the derivative does not exist. So step 1, we need to find our min and max. Get up there. So let's take our derivative, f prime. This looks like a little chain rule. Bring the exponent down front, 2/3. We have our inner quantity unchanged. New exponent 1 power lower, negative 1/3. Chain rule needs satisfied, so we will derive the inner function here and get a 2x. Okay, so let's see here. Our final derivative will be a fraction. 2x is over 1 multiplied by the 2 here, so we have 4x in the numerator. Our denominator has a 3 in it, and then we'll have this quantity. I'm going to put it back under a third root. Third root, and under that radical is x squared minus 4. So f prime of x, there's our derivative. And I guess I can get rid of this. Okay, and again, now to find the critical numbers, we set our numerator separately equal to 0. So 4x equal to 0 gives us x is 0. Now to get this one equal to 0, I could set it equal to 0. We'll divide out the 3, so the 3 is gone. We'll cube root both sides. 0 cubed is 0. So we're left with x cubed, or x squared minus 4. Add the 4, take the square root. We get plus and minus 2. X equals plus minus 2. So let me make my little chart here a little bigger, and let's get our intervals in there. We always start farthest left at negative infinity. We'll go to the smallest critical number, negative 2. Next interval picks up at negative 2, and we'll go to the next critical number, 0. And then 0 for the next one starts, and that goes to 2. And our final interval, 2, infinity, and beyond. Okay, so there's our test values, or our intervals. Let's pick our test values. First one here, good one will be negative 10. Negative 2 to 0, we're going to go with negative 1. 0 to 2, 1 looks like it fits in there. And 2 to infinity, we'll do a nice whole number 10. And let's see, I guess, well, I'm going to move this derivative down here so it's a little more accessible, sort of right there. And what we're going to do is figure out, I'll do it right on top here. We'll figure out if the numerator is positive or negative, and then the denominator. And then our sign will go in here, and then the conclusion. So negative 10 up here, 4 times negative 10 is negative. Now watch this. All the action occurs under the third root radical. Put in negative 10 and square it, that's 100. 100 minus 4 is positive. Cube of a positive is positive. 3 times a positive is positive. So our denominator is positive. Again, it's really what occurs under that radical. Negative numerator, positive denominator tells us our sign will be overall negative, and our conclusion, function decreases. Okay, next one, negative 2 to 0, we pick negative 1. Negative 1 times 4 is negative. Under the radical, negative 1, we're going to square that, so that's 1 minus 4, and that's negative under the radical. The third root of a negative is negative. 3 times a negative is still negative. Negative divided by negative is positive. Function increases. Okay, 0 to 2, we picked 1. 4 times positive 1 is positive. Under the radical, positive 1 squared is 1, minus 4 is negative 3, and then that's negative under the third root. Cube of that is negative. 3 times that is still negative. Oop, that's my denominator up here. What am I doing? Negative. Positive divided by negative is a negative derivative, and that tells us our function is back to decreasing. Final interval 10 goes in. 4 times 10 is positive. 10 squared is 100 minus 4, that's positive. Cube of that is positive. 3 times that is still positive. Function is back to increasing. Okay, this might be a good time to point out too. Let's go back to the original function. Remember, our theorem says we have to be continuous, a continuous function. This function f of x is continuous. You know, it's got a fractional exponent. We did not get a denominator that could zero out until after we derived. So this function is continuous everywhere. And that means we can have mins and maxes even where it's not differentiable. So where our denominator is zeroed out, the plus and minus 2, we might have, a sharp cusp. But the function is continuous because the original function, the way it was set up. And let's figure out if we got mins or maxes. So right here at negative 2, something was going on. We went from decreasing and then we went to increasing. So that is going to be a relative min. Here at 0, something was going on. Let me switch to red ink. To the left, we were increasing like this. And then we hit that point, and then we went to decreasing downhill. So that is a max, a relative max at x is 0. And then here something was going on at 2. To the left of 2, we were decreasing. And then we hit that point. On the other side, we went back to increasing. So that is going to be a relative min. And the real graph of this would look something like this. And again, at negative 2 and 2, where the derivative would have a 0 denominator, we have these non-differentiable cusps. And the 1 point where we set the derivative equal to 0, that came from our numerator. That would have a horizontal tangent line because our derivative would equal 0 at that point. Okay, on to the last example. This one has a nice little twist that might catch some of you on the test. Note that in those first two examples, the given functions are differentiable on the entire real number line. For such functions, the only critical numbers are those for which the derivative is 0. Example 3 contained a function with two types of critical numbers, those for which the derivative was 0 from the numerator, and those for which the derivative was non-differentiable from the denominator. When using the first derivative test, be sure to consider the domain of the function. For instance, the function in the next example is not defined at x is 0. This x value must be used for the critical numbers to determine our intervals. Okay, so let me just make this a little bigger. It says find the relative extrema of this function. So we could dive right in and start doing the derivative and finding the intervals and testing them. But again, let's check out the original function, f of x. It's not continuous everywhere. When our denominator is 0, we would have a vertical asymptote. So at x is 0, we know right now, before the problem begins, that we're not going to have a min or a max there. Sometimes if we forget to do this at the beginning of the problem, we might find a min or max that doesn't exist because it looks like one might be there, but remember the original function is not defined at x is 0. Okay, let's get started. Now, if you're looking at this and thinking quotient rule, you could go down that road. There will be a lot of simplification at the end of it. My personal preference, and you don't have to do this in your notes, you can do quotient rule if you want. Oops, I don't want that prime on there. I'm just going to rewrite this function. X to the fourth over x squared, that term would just divide to an x squared. And then I would have a plus 1 over x squared. I can write that as x to the negative 2. I would rather derive this and then turn it into one fraction after the deriving is done. But again, if you want to derive with the quotient rule, go right ahead. So let's derive first term 2x. Here we're going to bring that exponent down. That's going to be a negative 2x to the negative third power. And let's get rid of that negative exponent and turn this into one single fraction. So that's going to be 2x. I'm going to put that over 1 minus 2 over x to the third. That's supposed to be a 3. It's ugly, but you get the idea. So common denominator, 1 times x cubed is x cubed. And then we have a 2x times an x cubed. That's a 2x to the fourth. 2x to the fourth. And then the minus 2 times 1 is just minus 2. And now I can erase this and this. All right, and I'm going to put my final derivative up here, but I am also going to factor a 2 out of that numerator. 2, and then x to the fourth minus 1. Now, I look at x to the fourth minus 1. We could factor that farther, x squared plus 1, x squared minus 1, and then an x plus 1 and an x minus 1 from the difference of squares. But remember, we're just going to put test values in here. It won't be hard to put in a number and fourth power it and minus 1. Much easier than going through multiple different individual terms. Okay, numerator equal to 0. X to the fourth minus 1 equal to 0 means x to the fourth is equal to 1. And I can square root this side and get x squared. And then over here, plus and minus 1. We can't square root the negative 1, but we could square root the plus 1 and get the same plus and minus 1. So that just leads us to two critical numbers, plus and minus 1. Those come from the numerator. Those would zero out the entire derivative. But then we can also just set our denominator equal to 0 and get x is 0. So we have, again, three critical numbers. Let's find our intervals. Negative infinity to the lowest number, negative 1, and then negative 1 to 0, 0 to 1, and 1 to infinity to finish it off. So this looks a lot like a problem we had a little bit ago. First interval, negative 10 would be a good number. Here, negative 1/2 is in that interval. 0 to 1, we'll use positive 1/2. 1 to infinity, 10 will work nicely. So we're going to test again. I'll do my numerators and denominators up here. So negative 10 to the fourth power, that's a very large positive number. Minus 1 is positive, times 2 is a positive numerator. But when we put the negative 10 in the denominator and cube it, a negative cubed is negative. So that will divide to a negative derivative, and our function decreases. Negative 1/2 goes in now. Now, if we do, I'm just going to do positive 1/2 because we'll disregard the negative because it's going to square away. But if we multiply 1/2 times itself 4 times, that's going to be 1 over 4 times 2 is 8 times 2 is 16. When you square a fraction, they become smaller and smaller. So this is 1/16 minus 1. Again, the negative is going to be taken care of by the fourth power, and that becomes a negative numerator. And when we put the negative 1/2 in the denominator, it's going to cube to be another negative. Those divide to positive, and our function increases. Okay, let's put that positive 1/2 in. The numerator will stay the same. quarter, or half to the fourth minus 1 is negative, times 2 is negative. But when we put the positive half in the denominator, positive cubed is positive. So this is positive over negative, or negative over positive, which divides to a negative, and we decrease. Final one, 10 goes in, 10 to the fourth is huge, minus 1 is positive, times 2 is positive. 10 cubed in the denominator is positive. That is a positive derivative, telling us we have an increasing function. Now here, to identify the mins and maxes, we'll apply the first derivative test. So let's see here at negative 1, something's going on. And it looks like this wouldn't be hard to plug back into the original. Negative 1 to the fourth is 1. 1 plus 1 is 2. Over negative 1 squared is positive 1. So that's a point, negative 1 comma 2. Let's see what happened there. We went from decreasing to increasing. Decrease to increase means we have a relative min. Now, if we have forgotten that the original function is undefined at 0 on the graph, remember this is going to be a vertical asymptote. It's not going to be a min or a max, but it looks like we went from increasing to decreasing, increase to decrease. It would be very easy to think, oh, there's a max there, but it's not. That is a vertical asymptote. But it's easy to fall into that trap. Here, well, I guess we'd pick it if we did try to find the y value. If we plugged the y or the x is 0 into here, we would get a 1 in the numerator, but divide by 0. So if we were finding our y values, we might get a clue that that is not a min or a max. Finally here, at 1, comma something, if we put the 1 up into the original function, numerator 2, denominator 1, that's 1 comma 2. And we went from decreasing downhill to increasing uphill, so that is a relative min. So we've got two relative mins and a vertical asymptote in between. We can start to picture what this graph is going to look like. And there it is. It's kind of like two parabolas opening up with a vertical asymptote of the y-axis. And I think that is the last example. Yeah, the next time we are in class together, we're going to do some odd problems, and you can ask me questions on the WebAssign. I will see you then.